Hi guys, welcome to the final part of periodicity, so trends in the periodic table. So the third and final one we're going to look at for the moment is electronegativity. So this is going to be quite short because previously we looked at covalent radius and your ionisation energy. So again, the same two rules apply to electronegativity as well. So you need to be able to talk about how electronegativity differs for different elements in the periodic table in relation to their position and stuff like that, and explain why that is. So electronegativity we go into in a wee bit more detail in the next topic, so we're not going to do a massive amount on it in this video, but as long as you're aware of what it is, remember what it is, and then talk about the trends, then that's fine for the moment. So what we're kind of looking at here is bonding, right? So like I said, we've got a full other topic to do related to bonding, so we'll come back to this and we'll kind of get a deeper understanding behind it. But what we need to know just now is that electronegativity is a measure of an atom's attraction for electrons, right? So up until this point, you have been drawn chemical formula, you've drawn alkanes, alkenes, all that sort of stuff. You've just been drawn the bonds between the atoms. You've not really considered what that actually means. So at a higher level, we need to go into that in a wee bit more detail, and we need to consider what is actually going on with those electrons. So you know that a covalent bond is a shared pair of electrons. If you don't know that, then go back and look at your National 5 stuff. And as I said, we're doing more on that later. But what we've actually got is electrons that are not in a fixed position, right? So electrons are always kind of moving about, even whenever they're bonded to other atoms, okay? So even in a covalent bond, your electrons are still able to move. So what we're kind of interested in here is where the electrons are kind of likely to be in that bond, right? So depending on what elements are in that particular compound will depend on where the electrons lie. So this is where this electronegativity comes in, because it allows us to kind of predict where electrons are going to be in a chemical bond, okay? So this guy called Linus Pauling, so he was the guy that kind of came up with this. So 1932, he was kind of looking deeper into chemical bonds so that we could try and get a bit more information about what's actually going on whenever different elements are bonding together. So we've got another wee bit in the data book to look at, which is on the same page as your ionisation energies, so on page 11, which I've just popped up there for you just so that you can see what is going on. So obviously you've got your ionisation energy over here, and this wee column here is what we're interested in for electronegativity. So this is your Pauling scale. So these numbers basically just tell you that particular element's affinity for electrons, right? So for example, if we look at fluorine, so if we just go right across to fluorine, the electronegativity value is 4.0, okay? So that is actually the highest electronegativity value in the periodic table, right? So the higher the number, the more likely the electrons are going to be attracted to that particular element, okay? So if we look at something like sodium, right, and so the value for sodium is only 0.9, which is really low. So that means that electrons are likely to be moving away from sodium to something with a higher electronegativity value, okay? So what I would maybe do is kind of just familiarise yourself with this column on that page of the data book, and as we're going along, after this video we'll practice some questions using that as well, because it does come up quite a bit, and as I said, whenever we talk about bonding you need to be able to refer to this so that you can see what's going on. So in terms of what's actually happening, right, there's a couple of things which we'll get in more detail, but imagine we had two chlorine atoms, right? So your diatomic element chlorine, they obviously have the same electronegativity value, right? So if we had chlorine here and chlorine here, the electronegativity values are exactly the same for both atoms, right? So all that means is that these two bonding electrons aren't actually favoured on any of the sides of the molecule, okay? So what's going to happen is that the electrons are shared equally, so they'll be kind of somewhere round about the middle, and they'll probably not move that much. Okay, so remember in a covalent bond, what you've actually got is your positive nucleus, which is holding these electrons in place. Okay, so this is kind of important whenever we're looking at elements with a higher electronegativity. So, say for example, we had hydrogen iodide, right? So this time we've got elements that are completely different. And as I said, this is all still down to nuclear charge. It's to do with your number of electron shells as well, which we'll look at in a second. So again, looking straight at the data book, you can see straight away that iodine has got a larger electronegativity value, right? So basically it's got a bigger attraction for the electrons that are in this molecule. Okay, so again, the reason for that is because obviously it's got more protons, so it's got a higher positive charge in the nucleus than hydrogen would have. So what happens is that these electrons are kind of likely to be toward the iodine side, right? Whereas over this side, what happens is we end up getting this slightly positive charge over here, right? Because your electrons are kind of further over towards the iodine. And what happens as well over this side is that we get a kind of slightly negative charge. So that wee sign there is just delta negative, delta positive. So what you need to be able to do sometimes in the exam when you're answering questions is just label the part of the molecule that will be slightly negative and slightly positive. So we'll get a wee bit of practice at doing that as well so that you can see for yourself. So let's have a wee look in terms of the periodic table. So this is an important bit for this topic. We'll go into that previous stuff later. So we'll go for looking across a period. So we'll stick with lithium across to neon again. So the good thing is that you've actually got values for this in the data book, so you don't even maybe need to remember this trend, but if you have been understanding the nuclear charge stuff and if you've been understanding the electron shell stuff, then you shouldn't really have a problem with remembering it because it's the same stuff all the time. So looking at the data book, if you looked at lithium, your electronegativity value is just 1.0, beryllium 1.5, and then going along, you can see obviously that it's gradually increasing. So across a period, your electronegativity increases. Okay, so the reason for that is the same as all the other trends that we've looked at, because as you're going along, your charge in the nucleus increases, so you're getting more protons as you're going along. And therefore, if you've got a higher positive charge, so you've got more protons, it means that it's going to be, or it's going to want electrons more than the elements with less protons in it. Okay, so you've got a greater attraction because you've got a higher number of positive charges in that nucleus. Okay, so again, if you want to kind of pause this, take notes as you're going along, that's absolutely fine. Oh. So, going down a group this time, you could maybe actually guess what this is going to be. But if we kind of look at group 7, so fluorine, chlorine, bromine, iodine, again, looking at the data book, you can get your values straight away. So 4, 3, 2.8, 2.6. So going down the way, the electronegativity decreases. So the same thing is happening all the time. So because obviously as you're going down the group, the size of the atom is increasing, right? So it's getting bigger because you've got more electron shells. So what's actually happening is that the positive charge is further away from those electrons. So you've still got that shielding effect in there. So the bigger the element, the kind of further away those electrons are from the middle of that atom. So the kind of nuclear pull on those electrons is weaker. Okay, so that's why the electronegativity decreases as you're going down. Okey-doke. So, just to summarise, so across a period, electronegativity increases. So that's again same thing all the time because your nuclear charge is increasing. Down a group, electronegativity decreases because of your increased number of electron shells and that shielding effect. So always whenever you're doing explanations, on these questions is you're talking about the shielding effect and what effect that is going to have on that particular trend. Okay, so what we'll do, we'll stop there just now, and after this we'll try some questions on this before we move on to the next topic, which is bonding. So this seems very, very short, but like I said, we will definitely be using this going forward in the next topic. So as long as you're aware of what it is just now and what the trends are, then that is great. Okay, so we'll stop there just now and we'll see how we go on with that. So if you want to take a few notes on that, you can. And previously we kind of looked at the BBC Bite Size notes as well. You can do that if you find those notes helpful, because they are quite concise, just so that you don't need to keep pausing the video and things like that as well. Okay,